Here we're going to find the area of the part of the sphere that, given by x squared plus y squared plus z squared equals 4z that lies inside the paraboloid z equals x squared plus y squared. As I so often start, we are going to start by looking at the visual of this. Here's the paraboloid, but I think we need a little bit more before we can draw the sphere. So let's look at its equation. X squared plus y squared plus z squared minus 4z, leave a space, equals 0. We're going to complete the square by adding 4 to both sides. And so this becomes x squared plus y squared plus the quantity of z minus 2 squared is equal to 4. This is a sphere that has a center of 0, 0, 2 and a radius of 2, so it's tangent to the xy plane. And now I need to redraw the paraboloid. Let's give that another shot. I want it to look like the paraboloid is going to intersect the sphere in a circle, because that's exactly what it's going to do. Let's find the intersection of the sphere and the paraboloid. I think the easiest way out is to note that z is x squared plus y squared for the paraboloid, and we have an x squared plus y squared in the equation of the sphere. So the equation of the sphere becomes z plus z squared is equal to 4z, and you can manipulate that equation and see that that means that z is equal to 0 or 3. And we certainly don't mean the origin, so we're talking about where z equals 3. If z is equal to 3, then that means that x squared plus y squared is equal to 3. And so our trace in the xy plane is a circle of radius square root of 3. Now, what that means for us is two things. Number one, we're going polar. Number two, r goes from 0 to the square root of 3. We're going all the way around that circle because the sphere is all the way around, and so is the paraboloid, and so theta is going to go from 0 to 2 pi. Those will be our limits of integration. Now we need to deal with our integrand. We've got two surfaces, right? We've got the paraboloid and we've got the sphere. The area that we want is on part of the sphere. So we're looking for basically the cap of this sphere. And because the area that we want is the area of the sphere, we know we're going to use the equation of the sphere when we take our derivatives. In fact, I'll make a note here. We want the surface area of part of the sphere. Therefore, f of xy comes from the sphere equation, which we have at this point as x squared plus y squared plus the quantity of z minus 2 squared is equal to 4. Solving this for z is going to give us that z is equal to the square root of 4 minus x squared minus y squared, that square root plus 2, and we're going to say that that is equal to f of xy. Now we have our limits of integration in terms of r and theta. We have f of xy. That'll need to be in terms of r and theta. We have a formula for the surface area as a double integral. I'd like for you to see if you can make sense of all of it, figure out the area, come back when you're done. Go ahead and give this a pause. This is just going to be a progress check for you here. The partial with respect to x is negative x over the square root of 4 minus x squared minus y squared. The partial with respect to y, same thing except negative y over 4 minus x squared minus y squared in a square root. So, squaring those partials, adding them together, adding 1, and putting them inside of a square root, and getting common denominators for the plus 1 gives us the square root of x squared plus y squared plus 4 minus x squared minus y squared, all divided by 4 minus x squared minus y squared. X squareds and y squareds in the numerator subtract out. We end up with 2 over the square root of 4 minus x squared minus y squared. That's the point at which I convert this to polar coordinates. Negative x squared minus y squared is negative r squared. So our integrand is going to be 2 divided by the square root of 4 minus r squared. If you got this far just fine, cool. Just sit through the next 4 seconds when I have the graphic up. But for the rest of you, if this was a sticking point, then this is where you want to pick it up, put this together in the integral, and pause the video, come back when you're done. The rest of you, sit tight for the next 4 seconds. I'll be right back. The iterated integral that gives us the area of our surface is the integral from 0 to 2 pi of the integral from 0 to the square root of 3 of 2 divided by the square root of 4 minus r squared times r dr d theta. If you forgot the r, this was a rough ride. Remember, r dr d theta is our dA when we convert from rectangular into polar coordinates. We have a situation where we can split the integrand up into a function of theta and a function of r. The function of theta is 1, pretty straightforward. But here I've expressed it as the integral from 0 to 2 pi d theta times the integral from 0 to the square root of 3 of, now I multiplied and divided by -1, and I put the r up in the numerator with the 2. So I have negative of -2r over the square root of 4 minus r squared dr. That's because I'm thinking of 4 minus r squared as my u, therefore my du is -2r. I then integrate using the power rule. The square root in the denominator represents an exponent of -1/2. Add 1 to that, and I have a square root, and that exponent would be 1/2. Divide by that, we have this coefficient of 2. So the integrals equal 2 pi times the quantity of -2 times the square root of 4 minus r squared, evaluated from 0 to the square root of 3. Evaluating at square root of 3 for the r part is going to give me a -2, and evaluating at 0 is going to give me a 4. All told, this is going to be the area of the surface is 4 pi.